are swirling currents in a conductor due to a magnetic flux. They produce magnetic field by Land's law. So by Land's law, an eddy current creates a magnetic field that opposes the change in the magnetic field that created it. And thus, eddy currents react back on the source of the magnetic field. For example, as presented, a nearby conductive surface, which represents the can, which represents the conductor, will exert a drag force on a moving magnet. That's why it shows an opposing of motion. And due to this, it produces an eddy current that is induced in the surface by the moving magnetic field. That is why they are useful in holding spinning objects.
We know that the aluminum can and the magnet are not attracted to each other, such that the magnet does not pull the aluminum can towards itself, since aluminum is not magnetic. However, if we start moving the magnet near the aluminum can, or vice versa, an interaction takes place. The aluminum can starts moving. Part of that interaction is that the movement of the magnet is causing eddy currents to occur, which are whirling currents due to the magnetic flux that opposes the change of the magnetic field that made it, and thus eddy current react back on the source of the magnetic field.
Hi there, this is Karen, and I'm going to show you one of the many cases that reveals the anomalous yet brilliant functioning of the natural world. And guess what? It's magnetism.
Primary materials in this experiment are aluminum soda can and a medium-sized magnet. Others like pencil, clay, and wood are built as a base and a stand to where the can is placed.
Here's an interesting thing when we move the magnet near the aluminum can. We start seeing that an interaction takes place,
whereby the can starts moving back and forth as we continually move and swing the magnet near to it.
So there's some kind of interaction that's obviously happening here.
We know that aluminum is not magnetic, but if we have a magnet moving near the aluminum or vice versa, there will be some interaction, and part of that interaction is because of the movement that causes electrical currents to flow in the can.
That creates electrical field, which also creates a magnetic field because of the moving electrons. Given that aluminum is a metal, therefore a good conductor, when a magnetic flux linked to a conductor changes, a current is induced in the conductor. And this is due to the Faraday's law of induction. The conductor, or in this case, the can, will also encounter an opposing force and must do work because of the induced currents carrying electrons with it.
Within the can, however, the electrons making up the induced current do not follow one path. Instead, the electrons of that current within the can swirl as if they were caught in an eddy, or like a whirlpool of water, which is why it's called an eddy current. They are little circles of electricity or loops created and flows in such a way so that it can oppose the magnetic field, which forced a conductor to induce eddy current.
That, my friend, illustrates the Lenz's law. According to Lenz's law, the direction of the eddy currents is such that they create a magnetic field that oppose the changes that causes the currents. For this reason, the eddy currents must produce effective magnetic poles on the can, which are repelled by the poles of the magnet.
This situation gives rise to a repulsive force that opposes the motion of the can. The interaction between the eddy currents and the field causes the can to spin as demonstrated.
create and design a device that could crush an aluminum can using eddy current. What? Crush the can? Well, not physically, but using an eddy current. But how would we be able to do so? Well, it uses the very basic part of the lecture, magnetism. However, it mainly uses the repulsion of two magnetic fields. So, this was our group blueprint. First, you would wound a coil inside this lamp and connect this lamp to a switch and of course the capacitor or the battery. But you have to remember that the more voltage in the capacitor, the higher the possibility to crash or the can. So this capacitor would discharge an enormous amount of current through the coil, creating a magnetic field around it. As the flux lines pass through the cross-section of the can, current is induced and flows around the can. This induced current is called the eddy current. And this eddy current creates its own magnetic field, which repulses the magnetic field from the coil. Meaning, there is now two magnetic fields, and this magnetic field creates a force which pushes inward on the can and upward on the coil. It is strong enough that the can is crushed. Like I said, this is our blueprint. However, we were not able to obtain a capacitor that would be charged with a very high voltage. And so, we made another setup using a magnet and of course a can. This magnet, as we know, has a magnetic field, and when you move it across the can or along the can, this would distort the electrons inside the can, and this would mean that there is a moving electron or a moving current inside the can. This moving electron would induce a current. So this induced current, because it has change in magnetic flux or change in the magnetic field, it means that its zero value would turn into a finite value, creating or inducing a current. This induced current is called the eddy current. So this has a magnetic field, and the induced current also induces a magnetic field. These two magnetic fields would oppose one another, causing, of course, a repulsion. And this repulsion is the reason why, well, the can spins. As we all know, that the direction of the eddy current is determined using the Lenz's law or the Fleming's right hand rule. And yes, that would be all. Thank you.
Hello, so today we're going to demonstrate and discuss how eddy current produced. So first of all, we need to define what is eddy current. So eddy current is a swirling and circling current in a conductor, which is the can due to the magnetic field produced by a magnet. So we have a can. The can has thousands of electrons in it, and we have a magnet that is composed. We all know that a magnet composed of North Pole and a South Pole, and the North Pole is a negative pole and the South Pole is a positive pole. So basically, the magnet creates its own magnetic field. So basically, the movement of magnetic field is coming from the North Pole to South Pole. But however, if you place a magnet near the conductor, which is the can, if you put a magnet near the conductor, the magnetic field will flow. The flow of magnetic field is from North Pole, passing to the surface or to the can, and the magnetic field will then cause a magnetic flux, and to the South Pole of the magnet. So basically, the magnetic flux exerts a force to the electrons inside or in the can. So if the electron moves, the can will induce its own current. So since the flow of magnetic field is from the North Pole passing through the can and to the surface, to the South Pole of the magnet, the electron moves in a circular manner. So if the electrons move in a circular manner, it then called as the eddy current. The thing is, the eddy current produces its own magnetic field. According to Lenz's law, the magnetic field produced by the eddy current is the opposing field to the magnetic field produced by the magnet. So the relationship between the magnetic field of the eddy current and the magnetic field produced by the magnet, they are repelling each other. That is the reason why the can spins when you put a magnet closer to it. So the more rapid you move the magnet, the more fast the can spins.
Eagle double G.
Eddy's current, also called focal currents, are loops of electrical current induced within conductors by changing magnetic fields in the conductor due to Faraday's law of induction. Eddy's currents flow in closed loops within conductors in planes perpendicular to the magnetic field. They can be induced within nearby stationary conductors by time-varying magnetic field created by an AC electromagnet or transformer, for example, or relative motion between a magnet and a nearby conductor. The magnitude of the current in a given loop is proportional to the strength of the magnetic field, the area of the loop, the rate of the change of flux, and inversely proportional to the resistivity of the material. By Lenz's law, an eddy current creates a magnetic field that opposes the changes in the magnetic field that created it, and thus, eddy currents react back on the source of the magnetic field. For example, a nearby conducting surface will exert a drag force on a moving magnet that opposes its motion due to eddy currents induced in the surface by a moving magnetic field.
An eddy current is the current induced in little swirls on a large conductor. If a large conductive metal plate is moved through a magnetic field which intersects perpendicularly to the surface of the sheet, the magnetic field will induce small rings of current which will actually create internal magnetic fields opposing the charge. Eddy currents, or also called focal currents, are a loop of electrical current induced within conductors by a changing magnetic field in the conductor due to Faraday's law of induction. Eddy currents flow in closed loops within conductors in planes perpendicularly to the magnetic field. They can be induced within nearby stationary conductors and produce relative motion between a magnet and a nearby conductor. The magnitude of the current in a given loop is proportional to the strength of the magnetic field, the area of the loop, and inversely proportional to the resistivity of the material. By Lenz's law, an eddy current creates a magnetic field that opposes the change in the magnetic field that created it, and thus eddy currents react back on the source of the magnetic field. What I did to produce an eddy current is to have an aluminum can and a magnet. An aluminum can is a conductor, and what I did is to put the can in a stick to make it move freely. As we move the magnet in a horizontal motion parallel to the can, the magnetic field will pass through the surface of the can, which also produces magnetic flux. The magnet produces a strong magnetic field which disturbs the electrons in the can, causing it to move. When the current moves, its magnetic flux increases from 0 to finite value. This change in magnetic flux gives rise to induced currents in the can. The can obtains the same polarity of the magnet, hence the magnet is repulsed by the can and this causes it to spin. When there is a change in magnetic field, currents are induced in the conductor. This current is eddy current.